Most people think they understand how modern countries develop. They see tall buildings, fast trains, massive factories, and assume that progress is mainly about speed and visibility. But real national-scale engineering does not work like that. The most important systems are often the ones people never notice. Systems that operate quietly in the background, supporting everything else without asking for attention. China's greatest engineering achievements do not always rise into the sky. Many of them run across land, beneath cities, through mountains, and under extreme environmental conditions, working continuously without pause. This video is about one such impossible mega-project, a project that was not built to impress the world, but to keep an entire nation functioning. China is a country of extremes: extreme population density, extreme industrial demand, and extreme geographical imbalance. Some regions are packed with people, cities, and factories, while other regions hold the resources that those cities depend on. For decades, China tried to manage this imbalance using conventional infrastructure. Roads were expanded, rail networks were multiplied, and transport capacity was increased again and again. But there is a hard limit to how much traditional transportation systems can scale. Trucks consume fuel, trains require schedules, and surface transport is vulnerable to weather, terrain, and congestion. At a certain point, adding more vehicles does not solve the problem. It only makes the system more complex, more fragile, and more expensive to maintain. This is where Chinese engineers reached a critical realization. The problem was not speed. The problem was discontinuity. Resources were moving in batches instead of flowing continuously. Every stop, every delay, every transfer point introduced inefficiency and risk. What China needed was not faster transport, but a completely different way of thinking about infrastructure. Instead of asking how to move more resources, engineers asked how to create a system that never stops moving at all. A system that behaves less like transportation and more like a permanent operating organ of the country. Designing such a system is incredibly difficult because continuous systems do not tolerate failure. A truck can break down and be replaced. A train can be delayed and rescheduled. But a continuous national-scale system must operate every second, day and night, year after year. Even a brief interruption can affect millions of people and cause cascading economic damage. This meant that the project could not be designed using normal engineering standards. Every assumption had to be questioned, and every component had to be built with worst-case scenarios in mind. One of the first challenges was materials. Standard construction materials are designed for average conditions and scheduled maintenance, but this system would operate under constant stress. Temperature changes would cause expansion and contraction. Ground movement would introduce mechanical strain. Long-term operation would create fatigue that accumulates slowly but relentlessly. Chinese engineers responded by developing custom material standards. Steel alloys were selected not only for strength, but for fatigue, resistance, and thermal stability. Concrete mixes were adjusted to reduce micro-cracking under repeated stress cycles. Protective coatings were layered to resist corrosion, chemical exposure, and abrasion over decades of use. Material selection alone was not enough. Structural design had to account for the fact that the system would cross vastly different environments. In some regions, it would pass through deserts, where temperature differences between day and night are extreme. In other regions, it would pass through mountainous terrain where geological stability cannot be guaranteed. In densely populated urban areas, the system would have to coexist with existing infrastructure, buildings, and daily human activity. There was no single design that could work everywhere. Instead, the project became a collection of localized engineering solutions, each adapted to its specific environment, all integrated into one continuous system. Construction itself became a national-level logistical operation. This was not a single construction site with a clear beginning and end. It was hundreds of sites operating simultaneously, often hundreds of kilometers apart. Components were manufactured in controlled facilities to ensure precision, then transported according to tightly scheduled logistics plans. Installation followed strict sequences because one section depended on the completion and alignment of another. A mistake in one location could introduce stress or inefficiency that propagated across the entire system. Coordination between engineers, manufacturers, and construction crews had to be flawless. Even after construction, the system could not rely on traditional inspection methods. Manual inspection is slow, expensive, and limited by human perception. Instead, China embedded monitoring technology directly into the system itself. Sensors continuously measure pressure, temperature, vibration, and structural behavior. This data is transmitted in real time to centralized control centers, where engineers analyze trends rather than waiting for visible failures. The goal is not to react to problems, but to predict them before they become dangerous. This approach turns infrastructure into a living system, one that is constantly observed, evaluated, and adjusted. What makes this project truly remarkable is not any single technical feature, but the philosophy behind it. China did not treat this as a construction challenge. It treated it as a long-term systems problem. Every decision was evaluated not just for initial cost, but for lifetime performance, reliability, and resilience. Redundancy was built into critical components so that failure in one area would not bring down the entire system. This level of redundancy is expensive, but at national scale, downtime costs far more than prevention. This impossible mega-project represents a shift in how modern nations think about infrastructure. It is not designed for visibility or prestige. It is designed for endurance. It is designed to operate quietly, efficiently, and continuously, supporting everything else without drawing attention to itself. And that is precisely why most people never notice it. But without it, the visible achievements of modern China simply would not be possible. To understand why this mega-project could not be built using conventional methods, it is important to understand how normal infrastructure is designed. Most infrastructure around the world is built with the assumption that problems will occur and that those problems will be fixed later. Roads develop cracks and are repaired. Railways experience wear and are shut down for maintenance. Power systems experience outages and are restored. These systems are designed around interruption. They expect downtime. China's project could not afford that luxury. Interruption was not an acceptable outcome. This single constraint changed every engineering decision from the ground up. One of the most difficult aspects of designing a continuous national-scale system is dealing with uncertainty. Environmental conditions are never perfectly predictable. Temperatures fluctuate. Ground shifts slowly over time. Materials age. When infrastructure is small, uncertainty can be managed locally. But when a system stretches across vast distances, uncertainty accumulates. Small deviations become large problems. Chinese engineers address this by designing for extremes rather than averages. Instead of asking how the system would behave under normal conditions, they asked how it would behave under the worst conditions imaginable. Earth movement, heat waves, prolonged stress cycles, and long-term material fatigue were treated as baseline assumptions, not rare exceptions. This philosophy led to heavy over-engineering in many areas. Components were designed with safety margins far beyond what would normally be considered economical. Thicknesses were increased. Reinforcements were added. Joints were redesigned to allow controlled movement instead of rigid resistance. This approach increases initial cost, but it dramatically reduces the probability of catastrophic failure. Systems where failure can disrupt an entire nation, prevention is always cheaper than repair. Construction planning became as important as engineering design. Because the project spanned enormous distances, construction could not proceed linearly from one end to the other. Instead, it was divided into segments that could be built simultaneously. Each segment followed identical engineering standards, but local conditions required local adaptation. Construction teams had to operate with a high degree of autonomy while still maintaining strict alignment with the overall system design. This balance between central control and local flexibility is extremely difficult to achieve, and it required an unprecedented level of coordination. Logistics posed another massive challenge. The materials used in this project were not standard off-the-shelf components. Many were custom manufactured to precise specifications. This meant that supply chains had to be carefully synchronized with construction schedules. Delivering components too early created storage problems. Delivering them too late caused delays that could ripple across the entire system. In harsh environments, such as deserts or remote mountainous regions, even basic logistics like fuel, water, and worker accommodation became complex engineering problems in their own right. As construction progressed, quality control became a central concern. In smaller projects, defects can sometimes be tolerated or corrected later. In these system, defects could not be allowed to accumulate. Every component had to meet strict performance criteria before installation. Inspection processes were integrated directly into construction workflows. Components were tested, installed, tested again, and monitored continuously from the moment they became operational. This level of scrutiny slowed construction, but it ensured long-term reliability. One of the defining features of this project is how it handles stress. All large systems experience stress, whether mechanical, thermal, or operational. The question is not whether stress exists, but how it is managed. Instead of attempting to eliminate stress entirely, Chinese engineers designed the system to distribute stress evenly. Flexible elements absorb movement. Expansion mechanisms accommodate temperature changes. Structural continuity prevents localized overloads. This approach reduces the likelihood of sudden failure and allows the system to age gracefully rather than deteriorating rapidly. Automation plays a crucial role in maintaining this balance. Human operators are excellent at making complex decisions, but they are not well suited to continuous monitoring over long periods. Machines, on the other hand, excel at detecting small changes that humans might miss. By embedding sensors throughout the system, engineers created a constant feedback loop. The system continuously reports its own condition. Pressure variations, temperature shifts, and structural responses are all tracked in real time. This data allows engineers to intervene early, often before any visible problem appears. However, automation alone is not enough. Data must be interpreted, and interpretation requires expertise. Control centers staffed by engineers analyze incoming information and make strategic decisions. Maintenance is planned based on predictive models rather than emergency response. This shift from reactive to proactive maintenance is one of the key reasons the system remains stable over time. Problems are addressed while they are still small, preventing them from escalating into failures. Redundancy is another critical feature. In conventional infrastructure, redundancy is often limited due to cost constraints. In this project, redundancy is treated as essential. Critical components are duplicated. Alternative pathways exist to reroute flow if necessary. Control systems are backed up by independent systems. This means that even if one part of the system is compromised, overall operation can continue. Redundancy increases complexity, but it dramatically increases resilience. What is often overlooked is the human dimension of this project. Despite its scale and automation, it is not a purely mechanical system. Thousands of engineers, technicians, and planners contributed to its design and construction. Their experience informed countless small decisions that never appear in official documentation. Choosing one material over another, adjusting a design to account for local conditions, anticipating a problem before it becomes measurable. These human judgments are embedded throughout the system, even though they are invisible once construction is complete. Over time, the system becomes more than infrastructure. It becomes institutional knowledge. Lessons learned during construction inform future projects. Standards developed for this system influence national engineering practices. In this way, the project does not just solve an immediate problem. It reshapes how China approaches large-scale engineering challenges in general. By the time this project reached full operation, it had already changed the way Chinese engineers think about infrastructure. It demonstrated that with enough planning, coordination, and long-term vision, it is possible to build systems that operate continuously at national scale. Systems that do not rely on constant repair. Systems that are designed not just to work, but to endure. And this is only one part of the story. Once a project of this scale becomes operational, the real challenge begins. Building the system is only the first step. Keeping it running smoothly for years and decades is where most large infrastructure projects fail. China's engineers understood this from the very beginning. They knew that long-term stability could not depend on human observation alone. The system was simply too large, too complex, and too continuous to be managed using traditional inspection methods. This is why monitoring and automation were treated not as optional upgrades, but as core structural elements of the project. In conventional infrastructure, monitoring is often reactive. A problem appears, someone reports it, and engineers respond. This approach does not work when failures can spread rapidly across a national system. China needed a way to see problems before they became visible. To achieve this, engineers embedded thousands of sensors directly into the structure itself. These sensors continuously measure pressure, temperature, vibration, deformation, and operational performance. Individually, each measurement may seem insignificant, but when analyzed together over time, they reveal patterns that indicate how the system is behaving internally. The real power of this monitoring network lies in data continuity. The system does not generate snapshots. It generates streams. Every second of operation adds to a growing history of information. Engineers do not just look for sudden spikes or obvious anomalies. They look for slow trends. A gradual increase in stress, a subtle change in temperature response, a minor shift in vibration frequency. These small changes often indicate deeper structural processes that would be invisible without long-term data. Automation turns this data into action. Control systems constantly compare real-time measurements with predictive models. When values drift outside expected ranges, alerts are generated. But these alerts do not automatically trigger shutdowns. Instead, they prompt analysis. Engineers evaluate whether the change represents normal variation, environmental influence, or the early stages of a potential failure. This layered decision-making process prevents unnecessary intervention while ensuring that genuine risks are addressed early. One of the most important aspects of this system is how it handles failure scenarios. Chinese engineers did not design the project with the assumption that nothing would ever go wrong. They assumed the opposite. They assumed that components would eventually degrade, that unexpected events would occur, and that rare extreme conditions would be encountered. The system was designed to absorb these events without collapsing. This is achieved through redundancy, segmentation, and isolation. Redundancy ensures that no single component is critical to overall operation. If one element fails or requires maintenance, another can temporarily take its place. Segmentation allows the system to be divided into manageable sections. If a problem occurs in one segment, it can be isolated without affecting the rest of the system. Isolation mechanisms prevent localized issues from spreading, protecting the integrity of the whole. Together, these features transform potential failures into manageable events rather than catastrophic disruptions. Long-term operation also introduces the challenge of aging. Materials change over time. Metals fatigue. Coatings degrade. Environmental exposure accumulates. China's engineers accounted for this by designing maintenance into the system from the start. Instead of waiting for components to fail, maintenance schedules are based on predictive analysis. Data from sensors is used to estimate remaining service life. Components are serviced or replaced before they reach critical thresholds. This approach reduces downtime, lowers repair costs, and extends the overall lifespan of the system. Another critical factor is adaptability. No matter how carefully a system is designed, future conditions will never exactly match original assumptions. Economic demand changes. Environmental patterns shift. New technologies emerge. China's project was built with the expectation that it would need to evolve. Control software can be updated. Monitoring algorithms can be refined. Operational strategies can be adjusted. This flexibility allows the system to remain relevant and efficient even as external conditions change. Human expertise remains central to this process. Automation handles continuous monitoring and routine responses, but strategic decisions require human judgment. Engineers interpret complex data patterns, weigh trade-offs, and decide when and how to intervene. Training programs ensure that knowledge is transferred across generations of operators. Documentation captures lessons learned from real-world operation. In this way, the system accumulates not only physical resilience, but intellectual resilience as well. The scale of coordination required to operate this project is difficult to overstate. Control centers communicate with regional teams. Maintenance schedules are synchronized with operational demands. Data flows across organizational boundaries. This requires standardized protocols, clear authority structures, and robust communication systems. Any ambiguity could lead to delays or conflicting decisions. China addressed this by integrating technical design with institutional design. The organizational structure supporting the system was engineered as carefully as the system itself. Over time, the project has become a reference point for future infrastructure development. Techniques developed here influence other large-scale projects. Monitoring strategies are reused. Material standards are refined and applied elsewhere. The project becomes a learning platform, generating knowledge that extends far beyond its original purpose. This is one of the hidden benefits of building at such scale. Each challenge overcome expands the country's engineering capability. Perhaps the most remarkable aspect of this mega project is how unremarkable it appears in daily life. It does not demand attention. It does not announce its presence. It simply works. Day after day, year after year. This quiet reliability is not accidental. It is the result of thousands of design decisions, countless hours of analysis, and a philosophy that prioritizes endurance over spectacle. By the time most people notice infrastructure, it has already failed. This project was designed so that people would never have to notice it at all, and that may be its greatest success. When we step back and look at this impossible mega project as a whole, it becomes clear that its true achievement is not any single technical innovation. It is not the materials, the machines, the sensors, or even the scale. The real achievement lies in how all of these elements were integrated into one coherent system. This project represents a level of coordination that goes far beyond construction. It is coordination between geography and engineering, between technology and human decision-making, and between short-term execution and long-term vision. Most countries struggle to maintain infrastructure over time. Projects are built, budgets are exhausted, and maintenance becomes an afterthought. Over years, systems degrade, efficiency drops, and failures become more frequent. China approached this project from the opposite direction. Maintenance was not something added later. It was embedded into the system from the very beginning. Every design decision considered how the system would behave not just in its first year, but in its 20th and 30th year of operation. This long-term thinking is rare, and it is one of the reasons this project continues to function reliably. Another critical lesson from this project is the importance of accepting complexity rather than avoiding it. Simplest systems are easier to understand, but they are often less resilient. China chose to embrace complexity where it added value. Redundant pathways, layered monitoring, adaptive control systems, and flexible structural elements all increase complexity, but they also increase the system's ability to survive unexpected conditions. Complexity was not treated as a risk. It was treated as a tool, carefully managed and controlled. This project also challenges the idea that infrastructure must always be visible to be meaningful. Many of the world's most famous engineering achievements are celebrated because they can be seen. Bridges, towers, and monuments attract attention because they dominate the landscape. But this project operates largely out of sight. Its success is measured not in photographs, but in uninterrupted operation. People do not stop to admire it because there is nothing dramatic to see. And yet, it supports millions of lives every single day. This quiet reliability may be the highest form of engineering success. There is also an important institutional lesson here. Engineering alone is not enough to sustain a system of this scale. Organizational structures, training programs, and decision-making processes are just as critical. China invested heavily in building teams capable of understanding and operating this system over the long term. Knowledge was documented, shared, and updated. Experience gained during operation fed back into design improvements. This created a cycle of continuous learning, ensuring that the system evolves rather than stagnates. Over time, this mega project has become more than infrastructure. It has become a foundation for future development. The technologies tested here influence new projects. The standards developed here become national benchmarks. The confidence gained here enables even more ambitious undertakings. In this way, the project extends its impact far beyond its original purpose. It becomes a platform for growth, experimentation, and innovation. What makes this especially significant is that the project was not built during a moment of abundance or ease. It was built in response to real constraints. Geographic imbalance, resource pressure, and growing demand forced China to confront problems that could not be solved incrementally. This necessity drove innovation. When incremental solutions fail, systems-level thinking becomes unavoidable. China's response demonstrates what is possible when a nation commits fully to solving a problem rather than postponing it. From an engineering perspective, this project redefines what it means to build at scale. Scale is not just about size. It is about integration. It is about ensuring that thousands of components behave as one system. It is about aligning materials, machines, software, and people toward a single operational goal. This level of integration is extremely difficult to achieve, and it requires patience, discipline, and long-term commitment. For viewers trying to understand why this project matters, the key takeaway is simple. Modern civilization depends on systems that we rarely think about. When those systems work, life feels normal. When they fail, everything stops. The difference between stability and crisis often lies in decisions made years or decades earlier. This project shows what happens when those decisions are made with care, foresight, and respect for complexity. As global challenges increase, more countries will face similar problems. Growing populations, uneven resource distribution, climate pressure, and infrastructure aging are not unique to China. They are global issues. Projects like this offer a glimpse into how future societies might respond, not with quick fixes or isolated solutions, but with integrated systems designed to endure. This is why understanding projects like this is important. Not because we will all build identical systems, but because the principles behind them apply everywhere. Long-term thinking, preventive maintenance, data-driven operation, and respect for uncertainty are universal lessons. They represent a shift from reactive problem-solving to proactive system design. And perhaps the most important lesson is this: the most powerful engineering achievements are not always the ones that look impressive. They are the ones that quietly keep working, day after day, without demanding recognition. This impossible mega project does exactly that. It works, and in doing so, it supports everything else. If you found this breakdown useful and want to understand more about how modern nations solve impossible engineering problems, then make sure to stay connected. Videos like this take time to research and explain properly, and there are many more systems like this operating silently around the world. Subscribe to the channel, support the content, and let us know which mega project you want to explore next. Because the most important engineering stories are often the ones hidden beneath the surface.